the second part of the talk, we will review what is the connection Laplacian and its kernels and some important inequalities that we'll be using. So the connection Laplacian is also known as the rough Laplacian. It is a differential operator that's acting on the tensor bundles. It is defined as the trace of the second covariant derivatives. Here we have the definition, and for our work, we will be considering the connection Laplacian on the tangent bundle. Okay, and here we go. So here this Laplacian symbol, it's not Laplace Beltrami operator. Here we denote this as the connection Laplacian. Okay, so let's say xi are the eigenvector fields of the connection Laplacian with associated eigenvalues lambda I going from small to large. And these eigenvectors are L2 normalized, so their L2 norms are equal to 1. Okay. So with these eigenvectors, the heat kernel of the connection Laplacian can be expressed as this sequence expression. And for this heat kernel operator, we can find its Hilbert-Schmidt norm. So the square of the Hilbert-Schmidt norm here is can be computed using this series down here. Okay. So notice here that it's so both the Hilbert-Schmidt norm and the heat kernel operator, they are infinite series. So what we can do is we can just sum over the indices from 1 to a fixed number, let's say n. So in that case, then we can call it a truncated heat kernel and Hilbert-Schmidt norm of the truncated heat kernel, for example. And in that case, you just replace the infinity by n. And where are you gonna do the truncation? It's up to you. It's your choice. Okay, so like when you only do the finite summation, then you say this is a truncated heat kernel. Okay. And there's one thing that I want to point out. So notice that here, let's look at the Hilbert-Schmidt norm here. Okay. So the eigenvectors, they are L2 normalized. And the coefficient, we have a weight here. So it's exponential to minus lambda I plus lambda jt. So here there's an exponential decay. So as you can think that when I and j get very large, the weight is gonna be very small, like close to 0, right? So therefore, when you do truncation, you're really just getting rid of like a small error. Okay, so you can think that the full heat kernel can be approximated by the truncated heat kernel. Okay, so whatever we say that's about heat kernel, it's gonna be true for truncated heat kernel as well. I'm just not writing it down because otherwise it will look too complicated. Okay, all right. So then, what do we know about the Hilbert-Schmidt norm of the heat kernel? By Katel's inequality, we can see that the heat kernel, the Hilbert-Schmidt norm of the heat kernel can be bounded by the heat kernel of the Laplace Beltrami operator. And here n is the dimension of the manifold. And this is very important. This is a very important inequality, because what this means is, because we know a lot about the heat kernel of the Laplace Beltrami operator. There's like a bunch of results under different conditions, and then you have like you have a Gaussian bound exponential decay, and with curvature conditions, then you can see even more. So here again, I'm just listing some work done by some people here. I'm not going to go through the names. You can see. Okay, so um, we can just think about the one-dimensional heat equation and think about its fundamental solution. So you can see there's a Gaussian bound or exponential decay. So the small the t is, the diffusion time, the faster the heat kernel drops down to that 0. Okay, like, like fast, I mean like in terms of distance. Okay, so by Katel's inequality, we can then see the Hilbert-Schmidt norm of this differential operator, so heat kernel operator, decays exponentially. And moreover, using the Schauder estimates, we can also see its gradient also decays exponentially. And this is the core inequality or the core bound that we use for proving the Min theorem. Okay, so I'm not going to go through the details, but just keep this in mind that when we talk about the Hilbert-Schmidt norm of the heat kernel or its gradient, we have a very fast decay.